All right. So in this part, I'd like to reflect a little bit on the history of the subject. So the application of operator theoretic methods in dynamical systems really comes from Bernard Koopman's inspiration from seeing how quantum mechanics was developed by Heisenberg, Schrödinger, and others in the 20s. So the idea in quantum mechanics was that the predictions can only be done on a statistical basis using a wave function whose evolution is defined by an operator. And so Bernard Koopman, who was a mathematics professor at Columbia University, proposed in his 1931 paper to treat classical mechanics in a similar way. And he said, he proposed that spectral properties of the associated operator, the operator that we defined, but we defined it for a larger class of systems. In the case of Koopman, he defined it for Hamiltonian systems that I briefly discussed in the introduction. So the idea was to use the spectral properties of that operator, namely the eigenfunctions and eigenvalues, and also elements of what we're going to call continuous spectrum, and we will define it as we go later on. Now, Koopman worked with von Neumann, a mathematician who was at Princeton at the time, and who is responsible for a lot of different elements of modern mathematics, but also for the architecture of the computer as we know it today. So they worked together and extended it to some degree, but those works, while they were used in mathematics and in ergodic theory, and they were also had some influence in physics. For example, if you look at between 31 and 63, the original paper was cited 25 times. That's according to Google Scholar, but you know, it gives you a measure of how much was done. And perhaps part of the reason was the geometric picture of dynamical systems, which was advocated by Poincaré, was quite successful, and people were using that as the basis of dynamical systems theory. Now, then things became even a bit worse for the operator theoretic approach, because Ed Lorentz's discovery of a strange attractor, of course, created a lot of interest, and the Poincaré picture as the basis of analysis in dynamical systems essentially exploded. Now, a lot of progress has been made, including proving that the Lorentz attractor is in fact chaotic. But some of the roadblocks associated with applicability of the geometric concepts is the high dimensionality of the problems. It's difficult to think in higher dimension, and abstracting things from lower dimensions to higher dimensions can help, but again, it's difficult. And then the necessity of understanding the behavior globally. We talked about transient dynamics. So if we want to develop the theory, non-equilibrium theory, so away from attractors in state space, we do necessitate additional tools beyond, let's say, the classical Hilbert space tools with respect to invariant measure. Now, the geometric approach, however powerful it is, its weaknesses are related to locality, because it very often requires perturbative expansions around a known geometrical object. And again, low dimensionality. It's hard to make progress in higher dimensional systems using such tools. It is also not so easy to compute. Geometric computations are not easy. While, as you're going to see as we move forward, most of the computations that we'll be doing in the context of Koopman operator are either sums of series or algebraic methods, so finding eigenvectors and eigenvalues of a matrix that approximates the Koopman operator. So that's an advantage because there is a lot of tools, applied mathematical tools, that we can use to do those computations. So the last 20 years have seen a lot of usage of this methodology. I just checked, and the Koopman's original work now has more than 1,500 citations, and 90+% come from the last 20 years. So really, it was only in the 90s that the potential for wider applications of this approach has been realized. And in this century, the trend of applications has continued. I'll show you some references pretty soon. And that is driven by the fact that the methodology is well adapted to modern data science problems. But also, it doesn't neglect the powerful backbone of the Poincaré approach. In other words, for dissipative systems and measure-preserving systems, dissipative systems, so for all of those, we have strong connections between the spectral properties, so in particular eigenfunctions, and the geometry of the state space. And an example of that kind of a result I've just shown you, that proposition that tells us that level sets of Koopman eigenfunctions give us invariant partitions. So that's been developed in a variety of references over the past 10, 20 years. And the approach has been shown capable of detecting objects of key importance in geometric study, but not locally, globally, in fact. Many applications have been done in the context of high dimensional evolution equations. So systems that are driven by partial differential equations, for example, but not only those. For example, in our lab, we have a joint work with Professor Elliot Hawk's group, and we're considering dynamics of soft robots. So Koopman operator theory has become kind of a de facto modeling tool for soft robotics. Why is it that it would be appealing in that context? Well, soft robots are not, the constitutive equations very often are hard to find. So you don't have an underlying PDE, partial differential equation, very often. And having a modeling tool that does not necessitate an underlying physical constitutive equation is, in that case, an advantage. And I tend to say, in those cases, operator is the physics. So the operator itself contains the physics, and the equation is an operator equation, evolution equation that is given, that is provided by the Koopman operator. So it certainly is useful as a modeling tool, coupled, of course, with associated numerical methods for developed for those contexts that rely really, quite a number of them rely on linear algebra concepts. So that's a bit of history and where the essential advantages of the methodologies based on the Koopman operators sit. Here are some of the references that I mentioned in this lecture. Three and 4 are the original papers by Koopman, the first one that defined the operator in the context of Hamiltonian systems, and then the follow-up with John von Neumann. Number 5 is the book by Losota and Mackey that provided an introduction of operator theoretic methods in a broadest way, I would say, since these original papers. And then in this reference here, the spectral methods were used to find invariant sets of dynamical systems, and a variety of other applications were pursued also in '94. And then this is a review done in 2012 of the work on the Koopman operator theory in dynamical systems up to that point. 8 is a book on Koopman operators in systems and control that also provides a set of papers on the topic that are split into kind of 3 components. One is the theoretical, the other one is numerical, and another one experimental. And then number 13 is a recent review that also contains some original material that came out in American Mathematical Society notices just this last year. References 9, 10, and 11 provide some connections between the geometry of, for example, invariant sets and periodic partitions that we discussed in the previous lecture with Koopman operator eigenfunctions. And then in reference 15, Peter Schmidt discovered the dynamic mode decomposition. At that point, it was not clear that this was related to Koopman operator theory. That was later pointed out in this paper here, number 14. And then the Koopman mode decomposition, the topic that we're for the first time going to see in the context of linear systems in this lecture, was pointed out in reference 12 here, and then reviewed a little bit later in reference 13. So that was the first publication on that topic.